Welcome to Fundamentals of Logic Part 2. In our Part 1 video, we covered vocabulary, propositions and statements, truth tables, the laws of logic including duality and substitution, and we started rules of inference. This video, we will pick up with rules of inference and then go into quantifiers, including quantifiers and open statements, rules of negating and logical equivalences, contrapositive, inverse, and converse, as well as proofs with quantifiers. We will pick up where we left off at rules of inference. It will be useful to have your handout with the laws of logic and the rules of inference nearby. This is the example we used in our last video. Establish the validity or show a counterexample. If Rachel becomes a supervisor and works hard, she will get a raise. If she gets a raise, she will buy a new car. She has not purchased a new car, therefore either she is not a supervisor or she did not work hard. And the first thing we did was convert this paragraph into propositions. Our first proposition P was Rachel is a supervisor, Q, Rachel works hard, R, Rachel gets a raise, and S, Rachel gets a new car. With those propositions, we can write that we are given P and Q implies R. In other words, Rachel is a supervisor and Rachel works hard implies she gets a raise. We also have the implication R implies S. If Rachel gets a raise, Rachel will get a new car. And then the last given we have is not S. Rachel does not have a new car. And we wanted to verify not P or not Q. Either Rachel is not a supervisor or Rachel did not work hard. Our first step was just to write the given. R implies S, as well as the second step, we used not S. From there we use modus tollens in step 3. Modus tollens is over here in our rules of inference. And what we see from modus tollens is if we have an implication but the conclusion is false, it must be that the premise was also false. So we have an implication in step 1. We have that the conclusion is false. So in step 3, we are going to conclude that our premise must not have held true. Step 4, we rewrite the given, P and Q implies R. Step 5, again we used modus tollens because we have in step 4 an implication. In step 3, the conclusion is false, therefore our premise must have been false. And then to finish, we distribute the negative using De Morgan, and we get not P or Q. Now we are ready to look at quantifiers. We will start with quantifiers and open statements. First, the definition of an open statement. A declarative sentence is an open statement if 1. It contains one or more variables, and 2. It is not a proposition, but 3. It becomes a proposition when the variable is replaced by an allowable choice. An example of an open statement is P of x. The number x plus 2 is an even integer where x is an integer. So we can see it fits this definition as it is a declarative sentence. It contains one or more variables, that is, it contains x. It is not a proposition. As it is written, the number x plus 2 is an even integer. We cannot tell if it's true or false. But once the variable is replaced by an allowable choice, then it becomes a proposition. So if we replace x with the number, say 2 is an integer, then we can say the number 2 plus 2 is an even integer, and we can evaluate that as true. Or we can replace it with x equals 3, in which case P of x, because 3 plus 2 is not an even integer, would be false. We will discuss two quantifiers. The first is the existential. It is written in shorthand with the backwards capital E, and you read it as there exists, or you can read it as for at least one. The second quantifier is the universal quantifier. It is written with the upside down A, and it is read for all. So I have the following examples for quantifiers. Let's say we're discussing integers and we have the open statement P of x is greater than 0, Q of x is even, and also t of x is divisible by 5, then we want to write in symbolic form these three statements. So we'll do the first statement first. At least one integer is even. So here, since we're talking about at least one, we're talking about an existential quantifier. So there exists an x such that q of x, okay, q of x being x is even. And another interesting thing about quantified statements is now, even without a particular x evaluated, because it's quantified, we can evaluate this statement as true because there is an x such that x is even, x equals 10 or x equals 2. The second statement, there is a positive integer that is even. Again, because we're talking about the existence of an integer, we're using the existential. There exists x such that it's positive and it is even. And this statement is also true. Then the last statement, if x is even, then x is not divisible by 5. Oh, this r doesn't belong there. I'm going to scratch it out. I don't think I can erase it right now. So this says, basically, it is making a statement if x is even, so it's making a general statement. So for all x, if x is even, then it is not divisible by 5. So not t of x. And this is a false statement because 10 is both even and divisible by 5. One last definition, the open statement p of x and q of x are called logically equivalent. If for all x, p of x logically implies q of x, that's the notation, when p of a, if and only if q of a is true for each replacement of a, we say p of x logically implies q of x. So now we've discussed quantifiers and open statements. We are ready to look at rules of negating and logical equivalences. On your handout, you will find logical equivalences and implications for quantified statements, as well as rules for negating. Here it is enlarged a bit. An interesting application of this is this rule for negating here. We'll take a quick example. Let's consider the statement, everything is bad. If we write this statement in a logical form, we would say p of x, where x is bad, and then our everything is bad statement becomes, for all x, p of x. Now let's think about what will happen if we negate this statement. So we have the negation of for all x, p of x. Now some people would say the opposite of everything is bad is everything is good. However, according to our rules of negation, the negation of for all x, p of x is the statement there exists x such that not p of x. So in other words, the negation of this is going to look like there exists not p of x. In words, we would say there is something not bad. You might even say there is something good. So again, the point is that the negation of everything is bad is that there is something not bad or there is something good. So all you need to prove that this statement, everything is bad, is false, is to find one thing that is not bad or one thing that is good. To say the opposite is everything is good is doing way too much. Another example, we will negate and simplify the expression there exists an x such that p of x or q of x. Next, I'm going to use my rules for negating, and I'm going to use the rule for negating there exists. This rule says that to negate there exists, you're going to convert it to a for all and then a not p of x. So first, I convert to a for all, and then I'm going to put a not, and then my expression. Next, I'm going to use De Morgan. So I've put my negatives in front of each expression, and my ors changed to ands. Last, I'm going to use my logical equivalence, which says if I have a for all outside a compound statement, I can then, or an and in particular, I can then convert it to a for all with for each simple statement. So here I have a for all not p of x and my for all not q of x. And again, I use that logical equivalence. This one over here. Another example, negate and simplify the expression for all x, for all y, x is greater than y implies x minus y is greater than 0. So I chose to go ahead and let p of xy equal to x is greater than y and q of xy equal to x minus y is greater than 0. You don't have to do it this way, but I just wanted my logical expressions to look a little simpler. So with my substitution and my negation, I have the negation of, for all x, for all y, p of xy implies q of xy. Again, I substituted p of xy for x is greater than y, and I substituted x minus y is greater than 0 with q of xy, and my justification for this entire step is the negate. Now my next step is I look at how to negate for all, and I get this rule over here on my rules of negating. I have to have a there exists, and then I negate my p of x. So here I changed to my for alls to there exists, and I negate my implication. And again, my justification is I used the rule of negating for all. For my next step, I replace this implication with a not and an or, and I use that logical equivalence to replace the implication with not and or. Next, I distribute my negative using De Morgan and changing my or to an and. Then I simplify my double negation using my law of double negation. And finally, I replace my p of xy and q of xy with what they represented before. Notice my q of xy, since it's not q of xy, I flipped the x minus y is greater than 0. It becomes x minus y is less than or equal to 0. And then I am done. So now that we've looked at our rules of negating and logical equivalences, our next topic will be the contrapositive, inverse, and converse. For the universally quantified statement for all p of x implies q of x, we define the contrapositive, the converse, and the inverse. So the contrapositive of p implies q is not q of x implies not p of x. The converse is q of x implies p of x. And the inverse is not p of x implies not q of x. The contrapositive statement is logically equivalent to the original statement. So in other words, the contrapositive, not q of x, implies not p of x, is true exactly when p of x implies q of x is true. They have the same truth table evaluations. The converse and inverse are not logically equivalent to the original statement. Our first example of the contrapositive, inverse, and converse. Write the contrapositive, converse, and inverse. Determine the truth of the statements. So the original statement will be if m is greater than n, then m squared is greater than n squared. First, the contrapositive. So the contrapositive, we want the negation of the conclusion implies the negation of the assumption. So here we're going to negate the conclusion. If m squared is less than or equal to n squared, then, and we want the negation of the assumption, m is less than or equal to n. And that is a true statement. We know this from our arithmetic. Next, we'll do the converse, which says we want the conclusion implies the assumption. So we'll start with the conclusion. If m squared is greater than n squared, then m is greater than n. And we also know this is true, again, from our arithmetic. Last, we have our inverse, where we want the negation of the assumption implies the negation of the conclusion. So we're going to negate the assumption. So if m is less than or equal to n, then, and we're going to negate our conclusion, m squared is less than or equal to n squared. And again, we know this is true from arithmetic. And just a reminder, because we are talking about the positive integers, which is why these are all true. And then just to go back, our original statement, if m is greater than n, then m squared is greater than n squared. That is also a true statement. So in this case, you would definitely expect the contrapositive to be true since the original statement is true. It just so happens in this case that the converse and inverse are also true. An example, write the contrapositive, converse, and inverse determine the truth of the statements. So we'll start with the statement, if m divides n and n divides p, then m divides p. Now I'm going to write this and introduce some notation. I'm going to write m, and this bar, this line, represents divides n, and n divides p. These two things imply m divides p. So that's our original statement, and we know this is true, and we know this is true from our arithmetic. Next, we're going to write our contrapositive. To do that, we're going to say not the conclusion implies not the assumption. So for this example, it's going to be not if m does not divide p, and this is the notation for does not. You do the divides and you put a line through it, implies m does not divide n, and now since this is the negation, you have to use your De Morgan still, so you'll switch that to an or, and n, or n does not divide p. Next is the converse that says we take the conclusion and we imply the assumption. So for this example, we're going to take the conclusion, m divides p, and we want to imply the m divides n and n divides p. Last, for the inverse, we're going to take the negation of the assumption implies the negation of the conclusion. So we're going to have the negation, which is going to be m does not divide n, and again we have to switch this to an or because we're using De Morgan to do our negation. N does not divide p implies m does not divide p. So which of these statements are true? So the contrapositive, which I just fixed the spelling for, the contrapositive we expect to be true because it's logically equivalent to our original statement, which is true. The proof is a little more complex, but I will show it to you on the next slide. The converse, we know that this is actually false. And to show you why it's false, I'll give you an example. So let's say take m is equal to 3, n is equal to 5, and p is equal to 6. So here's a counterexample. So this statement is not true. And the inverse is also false, again by counterexample. So false by counterexample with m equals 1, n equals 2, and p equals 3. On the last slide, I said I would show a proof. If m does not divide p, then either m does not divide n or n does not divide p. So I start just by rewriting my starting assumption that m does not divide p, just so that I am very clear and I have that staring at me. I am going to approach this proof by breaking this up into two cases, and my case is inspired here by the conclusion I wanted to prove. So I have the case where the first part, m does not divide n, is case 1. My case 2 is m does divide n, and clearly these two cases cover all possibilities and they're mutually exclusive. So let's start with case 1. Actually, this is quite trivial. If case 1 is true, if m does not divide n, then I know that the or over here is true, because for the or, either m does not divide n or n does not divide p. And in this case, I have m does not divide n. Case 2, if m divides n. So if our proof is going to work, if m divides n, so this part of our or statement is false, we need to show that n does not divide p. I do this by contradiction. Why did I choose to go by contradiction? Usually, I do a proof by contradiction when I find I cannot prove it in the straightforward manner. So I did try to do a proof for this, just to straightforwardly show that n did not divide p, but I was having difficulty. So I decided, well, let's try a proof by contradiction and assume that n does not divide p. If that's the case, then we have, since we're in case 2, we have m divides n, and we've also got our assumption now, n divides p. But by arithmetic, that means that m divides p. Also, just a note, in Chapter 4, we'll be able to do a formal proof of this. But for now, just from your arithmetic, you know that means m divides p. But that contradicts our starting premise, the one that starts our whole proof, which must mean, since there's a contradiction, that this assumption over here was incorrect. Since it contradicts our starting premise, our assumption n divides p must be true, and therefore n does not divide p, and again, we are done with our proof. One last word about the contrapositive, converse, and inverse. So if you know the implication P implies Q is true, the only other one that you can know is true is the contrapositive, because the contrapositive is the only one that is logically equivalent. If you draw up the truth table, it is the only one that has the same truth table every time. So the converse and the inverse, often people will make the mistake that if they know P implies Q, that they will then try to argue or justify something using the converse and inverse, but that is logically not correct. So, it might seem obvious to you here and now, however, it is quite common, and in Chapter 5, we do have a question, an example that I will give you, and quite often people will ask me questions and my answer will be, you can't argue the converse. So you'll see that in Chapter 5. So in the meantime, I am going to leave you the image to go with arguing the converse. It's a trap. And by the way, I'm really pleased that I could integrate this image into this presentation. Now that we've completed the contrapositive, inverse, and converse, we are ready for the last topic, which is proofs with quantifiers. Our last topic is proof with quantifiers. Earlier in the chapter, we had done proofs using the rules of inference. However, if you recall, the rules of inference are used with propositions. So when we have open statements, we need to do something so that we can use them. And in particular, we're going to use quantifiers. And that way we can have them as propositions and then use our rules of inference. The first rule we'll need is the rule of universal specification. If P of x is an open statement for a given universe, and if for all x P of x is true, then P of A is true for each A in the universe. The idea is that if it's true for all x, universally true, then it's true for any specific A, hence specification. The next rule we will need is the rule of universal generalization. If an open statement P of x is proved to be true when x is replaced by an arbitrarily chosen element C from our universe, then the universally quantified statement for all x, P of x, is true. And what this is saying is if we choose a specific example C, but it doesn't matter, we can arbitrarily choose our C. So any C that we choose, when we plug it into P of x, if it's always true, then we can generalize and say that P of x is true for all x. That's the universal generalization. So for proof with quantifiers, we will start with this example. Determine the validity. All male carriers carry a can of mace. Mrs. Bacon is a male carrier. Therefore, Mrs. Bacon carries a can of mace. And just a side note, the mail carriers, those are the people delivering your mail from the post office. So we are going to start, like we did with our other proofs, by putting these statements into propositions. But we don't quite have propositions yet because we have variables like Mrs. Bacon. So we're going to start with open statements. Our first open statement is going to be M of x, which is x is a mail carrier. And C of x is going to be x carries mace. Now we can see how everything starts to fit in. We're going to start our proof. Our first step is going to say for all x, M of x, if they are a mail carrier, then x carries mace. And that is our first premise from over here. So for all x, if x is a mail carrier, then they carry mace. Now we can think about how Mrs. Bacon fits in. Well, she is M of Mrs. Bacon. Oops, Bacon. And that's also our premise because Mrs. Bacon is a mail carrier. Let me clean this up. If you recall from our last slide, we had the rule of universal specification, which would let us take these kind of universal statements, the for all statements, and then would allow us to substitute in a specific example. So that's what we're going to do with our third step. In particular, we're going to substitute Mrs. Bacon so what we get is Mrs. Bacon, a mail carrier, implies Mrs. Bacon carries mace. And again, we're using universal specification. Again, we just plugged in a specific value for x. But now we have propositions. Number 2, number 3 are propositions, and they fit right in to our rules of inference. So we can complete this proof and say, therefore, C of Mrs. Bacon, using steps 2 and 3 and modus ponens. And I wrote modus ponens right here just so you can compare. We have our premise. We have our premise implies a conclusion. Therefore, we can conclude our conclusion. Mrs. Bacon carries mace. Our next example, determine the validity. All law-abiding citizens pay their taxes. Mr. Pelosi pays his taxes. Therefore, Mr. Pelosi is a law-abiding citizen. We can go through and make the open statements and then make them into propositions and then try to use our rules of inference to prove this. However, it's an invalid argument, an attempt to argue the converse. So if you do go and try to use the rules of inference, you will find that none of them will allow you to make this conclusion. Here we have another example without the words, but we have for all x, p of x implies q of x and r of x. We also have for all x, p of x and s of x. And we want to conclude for all x, r of x and s of x. I started with the 2 premise. And then because my rule of inference use propositions, I plugged in a value for x in each of my premises using the rule of universal specification. And I get p of a implies q of a and r of a, as well as p of a and s of a. Now using the rule of conjunctive simplification, I can take this and I can just take off the p of a. Using modus ponens, I can use step 3 and step 5 and conclude q of a and r of a. Again, using the rule of conjunctive simplification, I can take just the r of a from step 6. And another use of the rule of conjunctive simplification over here, I just take the s of a. Using the rule of conjunction, I can join 7 and 8 with an and. And then to finish, I can use the rule of universal specification. Since my a and s did not have any restrictions on them, I can say this holds for all x, r of x, and s of x, and thus I am done with my proof. There are 2 more rules we should consider, existential specification being the first rule. There exists an x such that p of x implies p of a where a is an element from the universe for which p of a is true. The next rule is existential generalization. S of a implies there exists x such that s of x is true. So the first one we'll discuss is existential generalization, since it's a little bit easier. We're saying if we know there's a value a that makes s of a is true, then we can make the statement, the existential statement, there exists a value x such that s of x is true, in particular s of a. The existential specification also is not that difficult. It's saying if you have the statement then there exists an x such that p of x is true, well that means there's some element, some specific element in your universe that you can plug in and you can get p of a is true. To see why the rule of existential specification has to be used with a little bit of care, we're going to compare it to the universal specification rule, which said if for all x, p of x is true, then p of a is true for each a in the universe. In other words, if we know p of x is true no matter what you plug in, then you can basically plug in any value a from your universe. Going back to our previous example, where we had 2 open statements, m of x, x is a mail carrier, and c of x, x carries mace. We then used the rule of universal specification, and we could plug in Mrs. Bacon. So using the rule of universal specification, we got m of Miss Bacon and c of Miss Bacon, and we went on to do our proof. Now, because the universal specification allows you to plug in any value of a, since it's true for all values, you could plug in anything you wanted in here, and in particular you could plug in the same variable into M and into C. Because we're no longer using universal specification, it's not true for any value we plug in. In particular, this statement is not true for C of 5. So unlike the previous example with Mrs. Bacon, we then cannot use any implication of M of x implies C of x because here our x's are not the same. We are not able to plug in the same value into M of x and C of x. And therefore we can't use them in a proof the same way we did our previous example. Our next example, we want to prove there exists an x such that not S of x is true, and we are given for all x P of x or Q of x. Also we are given there exists not P of x, there exists an x such that not P of x. And last, for all x, Q of x or R of x, oh, there's one more. And then for all x, S of x implies not R of x. I start my proof by taking my given. There exists x such that not P of x. And then I say, okay, well A, let's assume A is going to be a value that makes not P of A true. And I'm using my existential specification. Next, I take another one of my givens as step 3, and then in step 4, because it's the for all, I can plug in anything I want. And in particular, I take the A that makes not P of A true, and I plug it into my statement here. And I use the rule of universal specification to do that. So again, it's important to realize that this P of A is the same A that makes not P of A true. And again, you can do this because this is true for all x, so you can plug in any A you want. If this had been a there exists, you would have had to choose another value because the value A that makes not P of A true may not have been a value that made P of A or Q of A true. But again, because it's a for all, you can plug in A. And since I'm doing this for all my givens, I went ahead and I did this for the same thing for this given here. Since it's a for all, I can plug in any value I want, so I choose again the very same A. And actually, I should have been referencing the previous line whenever I used universal specification. This one referenced 2. There we go. Again, I did the same thing for my last given. I used universal specification. And now I start doing my proof using my rules of inference. So for step 9, I am going to get Q of A because I am looking at step 2 and 4. In step 4, I have P of A or Q of A, but I know that P of A is false, so it must be Q of A that is true. Next, I converted step 6 into a implication. Q of A implies R of A. Again, that's that equivalence relation. We often use the other way around, replacing the implication with a not and an or. And now I can use my implication. Q of A implies R of A, And I also know that Q of A is true, so that must mean R of A is true by modus ponens. So now I have S implies not R, but I also know that R of A is true, which must mean by modus tollens that not S of A is true. And finally, since it's true for some value of A, I can use existential generalization to say there exists some value x such that not S of x is true. So we have covered fundamentals of logic, which included vocabulary proposition statements, truth tables, the laws of logic, the rules of inference, and quantifiers, in particular quantifiers and open statements, rules of negating and logical equivalences, contrapositive, inverse, and converse, and proofs with quantifiers. I would like to thank Ms. Harris of Edinburgh High School for her memorable example, "If I am elected mayor, I will clean the streets." And also, I wanted to mention a story, Love is a Fallacy. It's very entertaining, almost not like math. It's by Max Schulman. I would highly recommend reading it. If you are in my class, it is in the class website. And if you are not, you can easily find it by searching for it on the web. Thank you, and I'll see you in class.